by one of your colleagues, one of your more senior graduate student colleagues, Mankoba Batshuayo, a fourth-year student. And I'm just going to turn it over to him and see what he has to tell us about.
All right, thank you for that introduction. I don't know if I'm more senior, but good to see everyone. The class is so much diverse than it was for me, for my group. And so let me just share my screen, and at any time, let me know if you can't hear me. You know, technology always works except when you need it to work. Okay. All right. So let's see. We can get that. Okay. All right. Let me know. Can you guys see my screen? Very well.
Yeah, we can see it.
Thumbs up. Okay. All right. So I'm gonna talk to you guys about research work that this is a project that I started this January, unofficially in December. Yeah, so this is kind of recent work. I thought it may be interesting to people. It's cutting edge work, according to my own opinion. But so let me just share with you what will be the outline. So basically, I'll tell you about, just talk to you about my research group. And my research is an intersection between many-body physics and quantum computation. And so, as you saw in the title, we're using quantum algorithms to sort of model fermionic many-body systems. And so you'll hear some bit of ideas on many-body physics. And then the model that we are using is, well, that we'll be applying these techniques to is called the Lipkin-Meshkov-Glick model, in short, LMG model. And by model, I want to say we basically mean the Hamiltonian. How many of you guys have already taken quantum 1 and maybe are taking quantum 1? Everyone? Okay, so we're gonna revise some quantum mechanics here. Everything is quantum, 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 quantum. And so even the computers we'll be using to run our models, it's a quantum computer. How many, maybe just by a show, how many have heard of quantum computers? Sorry, Carl, I'll just decline your request. Yeah, okay. So many people seem to have heard of quantum computers. That's great. And so you're gonna hear much of that. And I wasn't sure how much I should get into the details, but hopefully I'll strike a good balance, because this is not a colloquium. You guys are now, what can I say? You are now grown up physicists, so I need to give you some equations. And okay, so this is my research group. It's headed, the leader is Dr. Elena Litinova. I believe she's the one teaching you guys Quantum Mechanics 1. And some of our group members, this guy here, you see him, his name is Herrick. He used to be a student here at Western. He just graduated last year. And then the guy next to him is Yinu. He's a postdoc student from China. And the guy here, that's me. I'm just kidding. That's not me, but this photo was taken long back. We don't have a group photo because I joined the group during pandemic. So, and then so those are my nuclear many-body physics guys. And then on the quantum computation side, I work with this gentleman. His name is Ryan LaRose. I put group in quotes because we're not necessarily a group. I just ask him whenever I have question. He's a PhD student at MSU, and he runs seminars on quantum computation every Monday. If you're interested, you can go to his website and check that out. Okay, and so this is the draft of the paper that we're working on. Hopefully we'll finish this project this month or next month. And so my goal was to give you enough information to sort of understand this paper eventually when it comes out. Okay, so it's titled Solving the Lipkin Model Using Quantum Equation of Motion. All right, and so those are a lot of big words. Let's try to break them down. Just a bit of intermission. How many of you here have already decided and you know what research you want to do? Can you maybe send in the chat and just say, yes, that's me? Can't see, where's the chat here? All right, okay, well, I can't see the chat, but okay, I see now. All right, so, and anybody else, nobody else has decided what research, okay, so I only see one person, Abby. Okay, all right, okay, so my goal is to try to persuade you that this is good research to do and maybe also impress the chair that I've been doing work. But how many would be interested to explore quantum algorithms if you were given the chance? Okay, so I see people are interested in, okay, thank you, Tyler. Yeah, that's my guy. All right, and so what I was thinking, I was playing about this idea in the summer. Would you guys be interested in a series called Quantum Computation for the Curious? Basically, we'll just have a few hours a week, and I can share more details on this subject. If people would be interested in that, we can talk later on. Okay, and so I wanted to, before I get into the whole details, I wanted to tell you, when I was at your year, when I was taking these research seminars, the slide that changed my life, it was a presentation by Dr. Fermionic. And he showed me this graph. I'm gonna show you now, this graph. And this, by far, I think it's a most important graph for anyone to have at the back of your mind when you're doing research. And what you see here is, in the x-axis, is the complexity of the problems you're working on and the reward that you're gonna have out of that. And so I took the liberty to improve on a slide by dividing this into 4 quarters. And the first quarter is problems that are not so complex, you know, but they have some relatively good rewards. And the goal is to increase yourself by challenging yourself to get into this first, this quadrant I call number 1, where you're dealing with difficult problems with very high demand. And of course, now to classify the research that I'm doing now, I would put it right here, just not so complex, but very high reward. And the high reward is because not so many people are doing it. And my goal is to convince you guys to start thinking about that. And then this project, when we finish it, I'm gonna be now working on modeling. I saw somebody is interested in superconductors. So actually I'll be modeling a nuclear superfluidity. And that will be now somewhere there. So, and so if you are interested in all of this stuff, definitely you can just come check out our group. I'm sure Elena wouldn't mind if you just sit in and see what we do at some time. Okay. All right. So yeah, I'm running out of time, so let me move fast. Many-body physics. What can we say about many-body physics? So there are 2 general school of thoughts in many-body physics. The first is the reductionist, and the second is the emergence. And I want to present this very clearly, because even if you don't get all of the other details, at least get this idea because it's very, very important. I think every physicist should know that. Okay, so what does the reductionist view say? It says, well, we can model the system by studying the dynamics of the interaction of its fundamental components. By the way, it was Richard Feynman who said, if all the books in all the books, physics books in the world would get banned, and he posed a question, what would be the most important information? Let's say just one sentence will be saved for the next generation. What one sentence do you think will carry the most impact? Let me see if people can guess. You can write in the chat. What will be the one most important sentence if all the physics books will be banned? Let's see what people think. Well, I already told you Richard Feynman said it, so it must be very, very important. All right. He said this, that all things are made of atoms. And so this was a very, very important thing. So what he's saying is that knowing the fundamental constituents of all what makes up the whole universe is very important. And many people have done research in this line of thinking that if we know the fundamental constituents and we know how they interact with each other, we can then build on that. Okay, it turns out that it doesn't work at all cases. And I will tell you what the emergent approach says. It says, well, you don't necessarily have to model the dynamics based on its fundamental constituents. You can look at the emergent phenomena. So, and that's based on elementary excitation. It was the Nobel Prize physicist Philip Anderson who said more is different. What it means is that when you now have more things in a system, they show phenomena that you cannot just derive from looking on these fundamental constituents. All right, and so let's see how this works. And so now get ready for some equations. You guys are doing quantum physics 1, right? Let's start with a system that you know very well, a single particle. Okay, and so this is the Schrödinger equation. Now, a quick question: what are the solution for this system? So that means what is psi and what is the associated energy? Your quantum students. It's a free electron, doesn't have any influence. What is it? You can send on the chat. Just making sure everybody is active. It's a very simple problem, guys. Or you can just unmute yourself and speak. Yeah, the potential is 0. V is 0. Yeah. Yeah. V of x is 0. And so what is psi and what is E? All right, so you know this as a revision that psi is your plane waves, right? And then your energy can be expressed in terms of the wave number, which is quadratic in terms of the wave number. But remember, this system is not quantized, meaning that psi cannot be normalized, it's unbounded. And so to get quantization, what do? You put some boundary conditions, isn't it? And so once you set your boundary conditions, like this system where you have two infinite walls and the particles is confined between these 2 points, then now you can see K is now proportional to N, where N is an integer. And then now your energy is quantized, and then you have now your states, right? This is great. Now, what if we now add one more layer in this? Instead of V equals 0, we add a system that you guys know and love very well, is the harmonic oscillator. This is the physicist's darling. And so what happens is now, once you change your V with the potential for a harmonic oscillator, you still get the energy being proportional to n. And now note, is no longer quadratic. Remember previously, it was proportional to n squared. Now it's proportional to n. And this has tremendous properties. Well, I mean, this you calculate in the quantum class, how you get this wave function depending on the Hermite polynomials. It's not very important. But what's important is that because this is just proportional to n, then the idea is that we want to get states that we can then write them just in terms of n. And it turns out we can do that by doing a canonical transformation on these operators. You guys did classical mechanics, right? So this is how you do the canonical transformation. You transform, you then define a new operators, A, dagger, and A, and they satisfy some commutation relation. And now what you have done is you have transformed your Hamiltonian in terms of your P and X, momentum and position, now in terms of A and A dagger. And then now we have the famous called creation and annihilation operators. They follow all of those properties. And now here's the question. What is being created now? These are called creation and these are called annihilation. What is being created? You can say in the comment, what is being created? You may or may not win $10 if you answer most of my questions. Let me put money, people will be interested to answer. Just kidding. What is being created? Excited states, yes, yes. A particle, no, okay. And I like that answer, a particle, because that's what I was thinking. You only have one particle. This is a single particle. You only have one particle in this sort of potential. And what this is doing is now creating a quanta of energy. And that quanta of energy takes the electron from one state to another state, okay? So what you are creating, you are actually introducing quanta of energy in the system. And so this is very important because later on, you will now be actually creating particles. And these quanta of energy, which is what now we were alluding to, as it will become important as the excitation of the system. And this is where the emergence comes from, in some sense. All right, so let's now take a switch and look at the reductionist approach, and then I will tie this harmonic oscillator to emergence. Okay, are you guys ready? All right, so the reductionist approach, think about it as now, if you now have multiple particles, which is your electrons and your protons, I claim that the Hamiltonian that you need will have like 5 terms, and all of these terms basically are just the two are the kinetic terms of the nucleus and the electron, and then all of the Coulomb interactions between the two. And then so the problem is, can you calculate the wave function psi and E from here? And the answer is no. Why? Because there's like 10 to the power 23 particles within a centimeter cubed of volume. And if you just consider only the spin degrees of freedom, this is 2 to the power 10 to the power 23. It's a huge number. And it's like greater than all the numbers, all the particles we have in the observable universe. By the way, this number 1080, which is the particles observed, all the number of particles we have in the observable universe, just search on on YouTube how they find that number. It's a very important number. And so we know the reductionist method doesn't work. And so how does the emergent method works? And so the emergent method works says that instead of looking at all of the individual constituents, look at what happens when they vibrate. When they vibrate, they form what? Sound waves. And those sound waves are your what? Are your excitations, right? Your sound wave, like the harmonic oscillator. And so the analogy here is, you guys know the Mexican wave. So the constituent is the people. And so instead of thinking about the individual people to model the behavior of the people in the stadium, model how the excitation, which is the wave they form. Does that make sense? And how can we do this mathematically? I already told you is that we can connect this to the harmonic oscillator. And so now all of those excitations can now be modeled pretty much by using the harmonic oscillator. Okay, I hope that concept makes sense. And so precisely we can do that for bosons. And bosons, they follow this commutation relation. And I won't get into the details here, but basically we can now, starting from the ground state, we can now apply this operator and get all the excited state. And these are the excitons. Similar thing, we can do that for fermions. And fermions, by the way, this picture is important. I'll just spend some time showing you, is that if you have all the particles stacked up in this, then once you introduce, this is like the ground state, right? Now, once you introduce a quanta of energy, that's what you are creating. You excite one of this particle into the excited state. And what you do is you create a hole here. And then people talk about the whole particle states, right? And I just added there that fermions are described by the Dirac equation, which is a marvel. It's one of the wonders of physics. It's so marvelous that one of my undergraduate professor who supervised my my project, he had it tattooed in his hand. This is how important this equation is in physics. So similar thing, the creation and annihilation. What now you have to take note is that for fermions, there's this Pauli exclusion principle. So you can't have two particles occupy the same state. And that just changes the spin statistics of it. So that means when you exchange two fermions, you have this anti-symmetry. But here's the punchline, is that we can create all excited states if we know this operator. Okay, does that point very clear? And so let's summarize what I just told you. The key concepts in many-body physics is that you can either look at all the fundamental constituents, and we saw that it doesn't work. You just have too many particles to ever do that. You need the whole universe to do a calculation of just a cubic, a few cubic quantum system. And so the emergence allows you to shift the picture into looking at the excitations, all right? And we say that for bosonic system, the excitations are actually called collective excitations. The reason is they do not resemble the real particles they are formed out of. The example there is phonons, which I told you, vibrations form sound, and other. By the way, just Google how these things are formed. One system, when you come to fermionic systems, what we have is called quasi-particles. It's quasi because it's not really a particle on its own right, but because it's derived from the underlying. And so these ones, they have some resemblance. And so what I just showed you, the particle whole, it's called an exciton. For those who were there in the previous general club meeting, we saw bi-excitons. And bi-excitons basically mean you now have two of the particle whole state, if that makes sense. So in this picture, you basically have now two whole and two particle, two whole states. So those were biexcitons, and there was a guy presenting on how they measure this in the lab. All right. So I hope I've convinced you that this emergent approach, it works very well. Okay, now let's look at, this may sound like great math, but is this a pseudo particle? Yes, 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 yes. So yeah, sorry, Kyle, I just saw your comment now. And so yeah, so the particle whole pair forms a, you can say, a pseudo particle. They call it quasi particle. It's basically the same thing. And so the big application for this kind of work is in the area of quantum fluids. And so basically quantum fluids are things like your superconductors. I heard people here are interested in superconductors. Ultra cold atoms, when you cool down a system, it has this quantum effects, and many other systems. I'm just using this as an example to show you that we are just not dry theoreticians who are pondering on things that have nothing to do with the real world. But here's the key point I want to make, is that despite over 50 years of hard work and progress, there's still no general theory that accounts for strongly correlated many-body quantum system. We still don't have a theoretical framework to explain all these phenomena when we have quantum effects in many-body physics. And so I would like to briefly convince you that there is one good candidate, and that is called the equation of motion. Okay, and so I'll be very quick so that I can get to the fun part of quantum computation. And so this equation of motion, here's the problem. The problem is that if I give you a Hamiltonian acting on some excited state and to find E, the problem is that how can you diagonalize that Hamiltonian to get all the excited states and E? This is like the standard Schrödinger equation, all right? And so as I've convinced you, the emergence approach says that, well, since we already know that if I have the ground state, I can apply some operator to get the excited state, then for this problem, which is now a general problem, I can imagine if I have some general excitation operator acting upon some general ground state, I can get the excited state, right? And with a bit of algebra, you can show that all the excited states can be found by this equation. And this is what we call the equation of motion. So basically, it's just the expectation value of the Hamiltonian with some excitation operator. I know what you're thinking. If you are very much paying attention, you may be saying, wait a minute, there are two things I've speculated here. First, I've speculated this. So first, I need to guess what is this ground state. It's not so very obvious to always have a ground state, right? And the second thing is I have to guess the this excitation operator. And so this leads us, and then of course, then to solve this equation, I have to do a variation to minimize that. You will learn about that in quantum mechanics. And so the claim is that the way to approximate this excitation operator is to use a method called the random phase approximation. And what it does is that you just approximate it as a linear combination of two particle hole excitation, all right? And once you have that, the details are that you do the variation, you get equations like this where that is given. I'll skip those details for later. But the bottom line is that we can do that. Okay, so I'm coming to my project now. What am I doing? I just gave you the framework of the general field, what am I doing? So what I'm doing is I'm looking at a model which is called the Lipkin-Meskel-Glick model, basically just called Lipkin model. And what it does is that you can model many-body physics by looking at a system that has two energy levels. Okay, so what you are doing is you put particles in either energy level 1 or energy level 2, and so the goal is that you only restrict the kind of interactions that you have there. And so what LMG, they realize that if you look at this general Hamiltonian, I mean, it's like very huge. It's like 2 to the power n, where n is the number of particles. Very huge if you have so many particles. But you can reduce the symmetry. You can impose some symmetry to reduce the size of the Hamiltonian. And how you do that, basically, you define, I already gave you the answer here. So you define three, the Hamiltonian has 3 terms. The first term, H naught, just basically counts the difference between the number of particles in the top and in the bottom one. And for this case, if the top one, which is the +1, has 2 particles, the -1 has 5 particles. And so the H naught will have this overall value, okay? And then so H1 scatters 2 particles up, 2 particles down, and then H2 scatters 1 up, 1 down, okay? And so the idea is that we can, to solve this equation, what we do is we notice that we can transform this into your angular momentum operators, right? Where you have J, meaning the total angular momentum operators. And then our Hamiltonian will look like that. And actually, this is very easy now because we already know the commutation relation for this. We can now solve this exactly. And so there is an exact solution for this. You can look at it when you are interested. And basically, what now we have seen is that we have transformed a general Hamiltonian, which was order 2 to the power n, into order n, where n is the number of particles. And so this now justifies that, okay, we can use this model to sort of test if our quantum algorithms work. But of course, you can see that we are not just gunning for this toy model, which is the Lipkin model. We want to solve the general problem eventually. And the general problem is of order 2 to the power n. All right, so now in these few minutes, if you don't mind, I'll just be quick. Let's turn our gears to the quantum world. And so for those who haven't seen it, this is a quantum computer. This is just your laptop. And one thing that I want to say, these are just, a quantum computer and a classical computer are very, very different species. And to sort of emphasize that point, you can think of a classical computer as a snail and a quantum computer as an octopus. It's just a different kind of species living in a different kind of environment, operating in different kind of rules. I had one person recently say, hey, I have this code, can I send it to a quantum computer? And I'm like, it's different things. They have different kinds of instructions. Yes, you code them, but it's a whole different language. It's like a land animal and a water animal, they're very different. And so now, because they're different, does not mean we cannot draw similarities in terms of modeling them. Okay, so I'll just I'll probably skip some things and so classical mechanics, if you had a tennis ball, it would follow one path. But if you had a quantum tennis ball, we know that it follows multiple paths and you don't know which one is it. So it's like a probability thing. And so basically, classical things are deterministic, always at one point. Newton's equations are well. And then quantum rules is like probabilistic, totally different. A land and a sea animal, a superposition, Schrödinger equation, far, far different things. And so classically, we use bits, which is either use 0 or 1 to do processing. And quantum, as you can see, these are qubits. And this is an important thing, these are vectors, okay? So these are scalars, these are vectors. And so vectors, they leave what we call the block sphere, and then scalars are just numbers. Who cares about them? The important thing is that if you have 2 to the power n bits, you only need n qubits to do that. And just to show you, if n is let's say 10,000, that 10,000, yeah, maybe let's say 100,000. If you have 100,000, 2 to the power 100,000, that's like already an intractable problem. But then you just only have, you need that number of qubits. You can solve it nice and simple in a classical computer. And if you come to the class on the summer, we can talk details about this. Another thing I want to tell you is when you have now multiple qubits, you can have interference. And so interference, what it means is that some of the parts, they then cancel out and you no longer have them showing up in the final result. And this is what we call entanglement. And it's a very, very important thing in quantum computation. And so what we have, just as an example, if you didn't have any entanglement, you can have like 2 qubits being in a product state, given like this. But once you have entanglement, some of these states like 0, 1, 1, 0, they cancel out, they don't show up. That's because of the quantum interference. And so entanglement is a weird property. I don't have time to talk about it. It's what gave Einstein a headache. He died not believing this is true. And so, but then it's a very important ingredient. And so what do we use to model a quantum computer? The rules are, it's all probabilistic. That means our results, we need to repeat them many times to get a probability distribution. We use superposition and we use entanglement. And so now I'll skip the general structure of how we do this. So basically, there's a way now we manipulate these qubits, and there's a way we have a different architecture for that. And so putting everything together, basically, we use equation of motion and RPA as a framework for our many-body physics. And we apply that to particular problem, which is the LMG Hamiltonian, and we can solve it using a quantum computer. And if you can borrow me 2 minutes, I want to show you tentative results of what we ended up getting. Is that okay? All right. And so what we use, as I showed you in the paper, in our project, we are using the quantum equation of motion. And so the quantum equation of motion basically says we have a clever way of guessing this ground state using what we call a variational quantum eigensolver. And once we know that, everything else is already given to us by this framework. And so this is how it works. The VQE is sort of like you take the so it's a hybrid algorithm. What it does is that the initial inputs of how you want to minimize your function are sort of done by the classical computer, but the hardcore problem, which is the cost of the function, is done by the quantum computer. And this goes back and forth until you find the minimum value. And then now, once you find the minimum value, you then put that in there, get all the expectation of all those operators, then calculate that, now you get all the excited states. All right, so I want to show you some tentative results this is a work that I was doing recently, we're doing in our group, is once we apply VQE, if we had, this is like the exact result, if we model it without including noise, and as I maybe haven't told you yet, is that quantum computers at the moment, they have so much noise. And so we see that our LMG Hamiltonian, the energy, if we increase the interaction strength, it follows the same path, but it's very, very noisy. And the states here, 1,1 means both particles are in ground state. And this one means both particles are in excited states. And we see the ratio here is different. When you increase the interaction strength, actually, you see this side increasing and these sides decreasing. But of course, there's still some error. There are some states where they are non-physical, they appear in our results. Okay, so let me do some summary and conclusion. Okay, so the summary that I want you to take home is that many body physics, we need to use the emergent approach. And the most promising framework to do that is the equation of motion, which, as I told you, it's the most plausible one towards us having a general theory of many body physics. And random phase approximation, which is approximating that excitation operator, has been very successful above mean field calculations and other Hartree-Fock calculations. But we still need to go beyond that. There's still some problems. On the quantum computation side, it doesn't matter how advanced of a theory you have. If you can't solve it, you can't know whether it's right or wrong, right? So you need to solve it. And a quantum computer is giving us a tool to sort of solve these hard and complex problems. And so I do want to end in this grandiose state that the near future, everybody will be using quantum algorithms. So you better just start now. And with that, thank you for paying attention. I hope this was useful. I can now take questions.
Thank you, Mantoba. Any questions from the class? What's the biggest quantum computer operating now?
Yeah, that's a very good question. It depends on how you measure big. So the one that has shown the most result is a quantum computer from China, which operates on a different set of qubits. They operate using photons. And so they have been able to solve a sort of like a toy mathematical problem that the current supercomputers cannot solve in billions of years. And they were able to solve it within a few seconds. And so this has shown what we normally say is called quantum supremacy, where now quantum computers are able to solve problems that no classical computer can ever solve. And so this is showing that quantum computers are really, how can I put it? They are far superior.
How many qubits did that computer have?
And so here's that tricky thing. So because of the architecture, it wasn't necessarily using qubits in the traditional sense that we were using it, because it's using a collection of photons. And so if you were to give it a number, it will be about 53 or 60 qubits. And so, yeah, you basically need more than 50 qubits to do any quantum supremacy calculation. The 2 years back, and actually this what I'm sharing you, these were news that were published in December last year. And so this is a recent work. And so in 2019, Google also had their own results where they showed quantum supremacy. And so they are using superconducting qubits. So I know people are interested in superconducting, and so that's something we can chat about if you are interested. And so there are different architectures. Some people are using trapped ions, and so those who are interested in the experimental side and the engineering side, this is something you want to do. For me, I'm more focused on the theoretical side, that can we come up with models and can we solve them and see if the predictions match with what experiments find. And so I think, yeah, the best way for us to look at it as physicists is that quantum computers are an exceptionally powerful tool. And it's better we start learning them as quickly as possible.
Any other questions?
I guess I'm curious about programming quantum computers a little bit, and how, like, if we start switching to, you don't have to go into a lot of detail, but if we start switching to quantum computing, how will, like, the skills of people who know how to program now, how much will they have to, like, adapt to that? Is it a big change? Is it similar?
Actually, it's not a big change in terms of, because you program, we use Python and script. And so many of the functions are still the same. And so one of the things that becomes different is understanding that now you are dealing with things that have a different meaning. Okay, so basically here your input devices and then your CPU had this kind of meaning that you are manipulating just scalar numbers. But once you turn to the quantum architecture, then you are now dealing with vectors, and how you manipulate them has a different meaning. But how you code them using a Qiskit for the IBM quantum computer, and Google has their own programming language called SEC and so forth. It's just using Python basically, and you don't learn new programming skills, but the meaning is different. And so yeah, if you have done computer science and you have computer science skills, it just takes just a few lessons to get what everything means, and the programming structure is still the same. I do want to add though that currently how we program quantum computers, you write your code and then you send it via the cloud to an IBM interface, and then they convert that code into instructions they can send to the quantum computer. Those instructions could be like microwave pulses that changes a state which is 0 and makes it a 1, which is like an excitation, and vice versa, like, or a rotation and things like that. And so I think this will be the way things are done for a very long time. One of the things that people is, I don't know if you guys have heard this, many people think, oh, are we going to have a quantum computer like our iPhone? And the answer is no. No, they are different systems. You need to keep them very cool. And so that's another challenge. So we will just use the cloud to access them.
Okay, thank you very much. Next week, we will hear from Yinu, who was mentioned also. And so hopefully that will be interesting, just as interesting. Thank you very much, Mankoba. And we'll see you all next week.
Thank you.
Thank you.
Thank you so much.
Thank you.